welcome to my first video. Today we're going to be focusing on conservation of energy, conservation of kinetic energy, potential energy, and let's get to it. So, a small block with a mass of 1.5 kilograms starts from rest, meaning it's not moving, at the top of an apparatus shown, top of the ramp. It then slides without friction down the incline, around the loop, and into the final level section on the right. It then collides with a spring, which momentarily brings the block to a stop. The maximum height of the incline is 2.5 meters. The radius of the loop is 0.9 meters, and the spring constant is 90 newtons per meter. Alright, the first thing we should do is start labeling our diagram. So, the block is 2.5 meters up. And the radius of the loop is 0.9 meters. Remember, the radius is half the diameter. So from the center down would be 0.9 meters. And then another 0.9 meters to the top. So our important height would be 1.8 meters. Of the block, the mass of the block is 1.5 kilograms. And the spring constant is 90 newtons per meter. Okay, find the initial potential energy of the block. Okay, find the initial potential energy of the block. First thing we have to do is write the formula. So, potential energy equals mass times gravity times height. This is gravitational potential energy. PE equals, plug in numbers, mass 1.5 kilograms, gravity is the constant 9.8 meters per second squared, and the height is 2.5 meters. Calculator time. Potential energy equals mass times gravity times height, which is 1.5 times 9.8 times 2.5 equals 36.75. And that units would be the joule. Done. Next, we need to find the velocity of the block at the top of the loop. There's two different ways you can do this. First, we need to apply the conservation of energy. That means that the mechanical energy that you start with is equal to the mechanical energy that you finish with. So mechanical energy is potential energy plus kinetic energy. And that will equal the mechanical energy at the end. Expand these formulas out. Mass times gravity times the initial height plus the kinetic energy. When you start this block off, how fast is it moving? Because I don't like to do extra work. So if it's not moving, then I know that that's going to be 0. I'm not going to bother with it. Potential energy, mgh final, that would be at the loop right there, plus kinetic energy is 1/2 mass times velocity squared. And that's what we're looking for, is the velocity. think we're ready to plug in numbers. We're ready to plug in the values. 1.5 kilograms times 9.8 meters per second squared times 2.5 meters. Now, if we're really slick, we could just take the answer from the previous problem and plug that in right there. But I'm going to work through a whole problem for you. Mass times gravity times the height, the final height. Final height, remember, is 1.8 meters. 1.5 kilograms times 9.8 meters per second squared times 1.8 meters plus 1/2 times 1.5 kilograms. We can grab everything because I'm out of space and shrink it up a little bit. Make a little space and continue properly. So 1/2 times 1.5 kilograms times v squared. Okay, how do you do this? Solve one side. On the left, we got 36.75 joules. And now, okay, now we have to take out our fuzzy bunny calculator, turn it on, and we have a mass of 1.5 kilograms times 9.8 meters per second squared times 1.8 meters. And we have 26.46 joules of potential energy at the top of the loop, plus 1/2 of 1.5 times v squared, the kinetic energy. Half of 1.5 is 0.75 v squared. Take out the fuzzy bunny calculator again, and 36.75 minus 26.46 gives me 10.29 joules on the left, and that's equal to 0.75 v squared. This is kilograms, 7.7 kilograms. Not to worry about that too much. Out of space again, so we will grab everything and shrink it up one more time. And solve for v squared. 10.29 divided by, where's my divided by? 0.75 will give me 13.72. That sounds reasonable. That's what v squared equals. I don't want v squared, and I'm not going to try and take 13.72 to take the square root of that in my head. So that would be the second function, square root. I hope I got that. Nope, I didn't. Second function, square root. There we go. 13.72. And I get 3.7 meters per second, and that is what v equals. Is that reasonable? Yeah, that's not too fast, not too slow. That's a reasonable number. Good. All right, finally, find the velocity of the block after it goes round the loop and the flat section of the path. All right, finally, find the velocity of the block after it goes round the loop on the flat section of the path. let's see, since we have zero friction, we don't have to even pay attention to the loop. It's as if the block went from the hill down to the flat section at the bottom. What does that mean? Well, I already know that there is no kinetic energy up at the top of the hill. And there is no potential energy at the bottom of the hill. That's going to make things a little easier for me, because I know that mechanical energy that I start with is going to be equal to the mechanical energy that I finish with. I don't have to worry about kinetic energy at the beginning. So the potential energy that I start with is going to be equal to the kinetic energy at the bottom of the hill where I finish. Expand the formulas. Mass times gravity times height equals 1/2 mass times velocity squared. And I plug in. I'm going to start off, I know I'm going to run out of room. So let's shrink it a little bit. .5 kilograms times 9.8 meters per second squared times 2.5 meters is going to be equal to 1/2 1.5 kilograms times velocity squared, what I'm looking for. Now I know that 1.5 times 9.8 times 2.5 is equal to 36.75 joules. And 1.5 times 1/2, that's equal to 0.75. And we're going to multiply that times v squared. 36.75 divided by 1.75. Use our fuzzy bunny. .75 divided by 0.75. 49 joules equals v squared. Now it's really important that you recognize that 0.49 would not be a reasonable answer. So I got to pay attention. 49, square root of 49. Square root of 49. That's a familiar number. Take the square root of both sides. And if you don't know, then you should. Use your calculator. 7 meters per second is your velocity. Finally, almost at the end, how much will the block compress the spring before momentarily coming to a stop? This looks like we got finally something a little bit different. So I know mechanical energy is going to be conserved. Mechanical energy that I start with is that I finish with. The mechanical energy that I finish with is going to be stored now as elastic potential energy. And it's not going to be moving, so I don't have any kinetic energy. It's all the way down on the ground, so I don't have any gravitational potential energy. So potential energy equals gravitational potential energy equals the elastic potential energy that I finish with. I know that the gravitational potential energy is 36.75 joules, and the formula for elastic potential energy is 1/2 kx squared. K being the spring constant, which we have, x being how far the spring is compressed. So now it's a pretty simple algebra problem. 36.75 equals 1/2 90 newtons per meter. times x squared. Looks very familiar. Bring out Fuzzy Bunny. 36.75 divided by half of 90, that's 45.81. Okay, yeah, that's reasonable. 0.81 equals x squared. If you're paying attention, you know that I wouldn't have let you say 0.81. Anyway, square root of 0.81, square root of 0.81, 0.9.